I will be talking about computational micromagnetics, methods, and software. First, I'll go over a brief description of what computational micromagnetics is, why we are interested in it, before talking a little bit about its historical development, before going into what actually a computational micromagnetics code is doing, and then finishing up kind of with some points about the future of the field. So we got a little bit of exposure to computational micromagnetics in this class where we used Mumax to do some simple homework problems. And typically in magnetics research, that is how it's used. It's a learning tool. It's something for people to understand the physics of their devices and what's going on. Of course, you can take measurements as well, but the nice thing about computational micromagnetics is you can create a lot of data. You can get really nice resolution, so you can get really nice visualizations. And you can really control what it is you're simulating. You can have perfect geometries, you can control whatever noise you want, so you can really kind of get into what is happening based on the physics to help you design devices. The goal of a computational micromagnetics code is to calculate the vector magnetization throughout the material. There are types of codes that go kind of further down into looking at atoms individually. There are codes that look at devices kind of like on a systems level. We're kind of between those two. We're modeling the magnetization throughout the material. And the way we do that is we solve the Landau-Lifshitz-Gilbert equation like we talked about in class. Now, if you've taken a course in differential equations, you've got a pen, paper, some time, you can, for very simple geometries, just do this by hand, but it gets out of our kind of abilities pretty quick, and we need computers to do the work for us. But you don't need to take my work for it. These are all examples in the last couple of years of papers on a bunch of different topics from magnetics that they use computational micromagnetics for their research. I like this video in particular. It shows a creation of a skyrmion kind of like in real time. So I think that's a cool visualization. But kind of across the spectrum of magnetics research, people use computational micromagnetics to assist with their understanding, assist with their design, and whatnot. So that's what computational micromagnetics is, and I'll talk a little bit about its historical development. People first started using computers to solve micromagnetics problems in the 1960s. They were looking at domain walls, but of course the problems were much simpler than we might look at today. These are one-dimensional problems generally, very few data points. You don't have a lot of memory for your computer. And I like this quote on the right side where they weren't even sure that it was going to be worth their time to run these simulations. It would just be a waste of effort. But of course, now we use it all the time, and it's largely due to the efforts that these people did. And actually in the 1970s, I point out this paper because it's very similar to what we did on our second simulation homework, where we're doing domain wall motion. And these are the problems that they were solving in the 1970s. Today, it's a homework problem in a class. But the big kind of breakthrough with the field was the release of the Object-Oriented Micromagnetic Framework, OOMF, in 1998. And this was the first time that people could, it was an open source software, so magnetics researchers who weren't experts in numerical methods and programming, they could download this code and use it for their own research. And so this kind of opened it up to magnetics researchers across the board. But what we used, of course, was Mumax. And the reason that that was a significant development was because it was the first free-to-use software that parallelized the computations using graphics processor units, GPUs. So that allowed much quicker computation. But of course, OOMF is still widely used. I think at one point, Dr. Incorvia had mentioned that she used OOMF during her graduate studies. So it's still a very modern code. It uses GPUs now as well. And then I've got a table here just kind of going up to 2018. There's just a bunch of different packages that are out there that people can use for research. And then people, of course, can write their own if they feel competent. So now I'll talk a little bit about what these different software packages are doing. Like I said, the goal of any computational micromagnetic software is to solve the magnetization vector by using the Landau-Lifshitz-Gilbert equation. To do this, we have generally two methods. We have a finite difference method, and we have a finite element method. Now, they've got a lot of similarities. They both discretize your geometry into unit cells, but they make different approximations during the process, and we'll talk a little bit about what those approximations look like. Now, in either method, the most computationally complex step is the computation of the demagnetization field, which is a little ironic because it was the first magnetic field kind of that we talked about in class due to shape anisotropy, so magnetic surface poles. But for the computer, this is a much more difficult calculation. They don't just get to look up in a table what the shape is and pull out a value for n. They actually have to kind of rigorously go through and calculate for each cell. This plot in the middle shows sort of the relative solve time for some of the different steps. And you see that the demagnetization field is just about the most complex step for either finite differences or finite elements. This solve preconditioner is something with the time integration. And to see why it is that the demagnetization field is the most computationally complex, let's first consider some of the other kind of things that are going on: crystalline anisotropy and the exchange field. Both of these fields, they use information that is local to the cells that you're calculating. So if I want to find the crystalline anisotropy, I just need to know the magnetization in that cell, and I need to know its direction of anisotropy, either uniaxial or cubic. And so if I have 100 cells, I'll do 100 calculations. If for exchange, I only need to look at their nearest neighbors. So if I have 100 cells, I'll do 600 calculations because I need to find the difference in the magnetization between the cells on each of the faces. So, but it's still linearly growing with the number of elements. For the demagnetization field, what I need to do is I need to calculate the interaction between every cell with every other cell. So this is a quadratically growing computational step. Handley goes into a little bit of a derivation for the volume poles, but we did the surface poles in this class. Our sigma was magnetization dot the unit normal at the boundary. So if you're interested in seeing the full derivation, you can go into Handley section 2.6, but you come up with this integral equation. This integral equation takes a volume integral over a derivative. And this is where the two methods diverge. For finite differences, what I'm going to do is I'm going to approximate the act of taking a derivative. So I'm going to take an approximate derivative, but my magnetization is exact, quote unquote. For finite elements, what I do is kind of before I take a derivative, I make an approximation to the magnetization so that I can take an easy exact derivative of it. A little bit more in depth of what that looks like. So like I can say in one-dimensional case, if we have a magnetization that we want to take the derivative of, if I want to find the derivative at some point, I can just look at the 2 points on either side, draw a line between them, and use that as my approximation for my derivative. This is a central differences formula. It comes from taking a Taylor series. This is something that's kind of universal to all kinds of solvers. So it's pretty easy to implement. For the finite elements method, what I do is I assign basis functions to all the nodes in my geometry. And in any cell, the magnetization is the sum of the basis functions which overlap with the cell. And these basis functions, usually we make them linear because those are easier to take derivatives of. So the magnetization in any cell is just the sum of the slopes of the basis functions which span the cell. So that's, a much more simple way of representing our magnetization to take the derivative of than some kind of complex function that looks like this. And of course now you can add whatever other fields and terms you want to your solver. People kind of take different amounts of these. Generally, none of them are going to take as much time to solve as your demagnetization field. Once we have the demagnetization, or once we have solved the Landau-Lifshitz-Gilbert equation, that everything we did gets us the solution at one point in time. So now we need to step forward. The nice thing about the Landau-Lifshitz-Gilbert equation is that we're solving for a slope, and so we can use that slope information to approximate the magnetization at the next step, and then again calculate the Landau-Lifshitz-Gilbert equation. In your one sort of to do this, these are called Runge-Kutta methods. The simplest Runge-Kutta method is just Euler's method, but generally they use higher order methods like a Runge-Kutta 4 method, which is what MUMAX actually uses. And now I'll talk a little bit about kind of the future of computational micromagnetic solvers. Of course, the obvious thing that we want to do is we want to solve bigger problems and we want to take less time to solve them. And this kind of has two ways of going forward. People are coming up with better methods using preconditioned methods, hierarchical matrix methods to build upon the finite differences and finite elements methods. But people also want to take advantage of new hardware. So using newer GPUs, or say some of the kinds of hardware that Sam and Maxwell just talked about, the neural network hardware, to be able to do simulations faster. People also couple the Landau-Lifshitz-Gilbert equation to other physical kind of phenomenon, such as to Maxwell's equations or even to Newton's equations as well. I think it was Elena that talked a couple days ago about magnetostrictive effects. And so these people couple the Landau-Lifshitz-Gilbert equation to Newton's equations to simulate an acoustic antenna. So it's a bulk acoustic wave antenna. And then people also then try and couple it to different scales of physics. So they might kind of couple the atomistic solver with the Landau-Lifshitz-Gilbert solver. And then people also use computational micromagnetics to generate data sets for neural networks. So in the middle here, these people did a bunch of micromagnetic simulations. They fed the data into a neural network. And so now for kind of new different configurations of magnetic grains, they don't need to run the computational micromagnetic simulation. They can just use their neural network to predict the coercive field and other kinds of things. And so it's going to continue to be used as a tool for magnetics researchers as the technologies improve and as we can simulate cooler and cooler things using it. To kind of briefly summarize what I talked about today, computational micromagnetics is both a tool and an area of research. It started in the 1960s, but really the big push forward was with the release of OOMPH in 1998. When you're, kind of any micromagnetics code is interested in solving the Landau-Lifshitz-Gilbert equation, which we use either finite differences or finite elements, and then we step forward in time with some kind of a Runge-Kutta method. Yeah, and so the future looks pretty bright. If anybody has any questions, I'm happy to take them.
Thank you so much, Andrew. Any questions?
I just had a quick question on one of the first slides where you had the video for the skyrmion being created. Just out of curiosity, do you know like what the time scale is on the video?
I'm not sure for this particular video, but usually when you're solving computational micromagnetics phenomenon, you're on the scale of picoseconds. So I don't know how long it took for one skyrmion to make, but I'm guessing it's on the order of picoseconds. So.
Any other questions?
I have a question about the solving method. So you mentioned there are two kinds of method. One is the finite element and another is the finite difference. So when solving this equation, does this program, the MuMax, choose one of the method automatically, or maybe it will use the combination of these two methods, or it is choose automatically? So I don't know.
Yeah, generally when you write a computational micromagnetic solver, you pick one of these two. And so MuMax uses the finite differences method and OOMPH does as well. Most kind of methods that people work on use finite difference methods. They're generally easier to implement for a programmer. You can use Fourier transforms to accelerate the computation. So it's not, the demagnetization field calculation isn't quadratic. It's order n times log of n, which is much faster. Although finite elements, I think in recent years, as people have gotten kind of newer mathematical methods and whatnot, is gaining a little bit of steam. But generally, most people, I think, probably use a finite difference method. You do get a little bit of choice over the Runge-Kutta method that you use to do the time integration at the end. But like I said, it defaults to a fourth order Runge-Kutta method. But you can go anywhere from like 1 to 6, I think, something like that.